I'd like to pick up where I left off in the last video talking about titrations. We were looking at these titration curves and the idea that weak acid titrations have a different shape than strong acid titrations, but parts of them are the same. Equivalence points end up in a different place. And the key idea there being moles equals moles. The moles of which you add is equal to the moles of which you started with. That's the basis of titrations. And if you can remember nothing else, remember that. So I'm going to zoom in a little bit on that particular definition, the idea that moles of what we start with is moles what we end up with, moles that we add. And in our case, for an acid-base titration, we're adding moles of our base, and we are coming up with moles of our acid. All right? So we're talking about acid-base titrations. In this particular case, for the picture that we have here, we're talking about acid titrations with a strong base. So we'll say titrating some acid with a strong base. And I know my color coding just went out the window. That's too bad. I'll throw in some blue just to balance it out. All right, if we're titrating our acid with our strong base, as we're taking a closer look at this titration, the drawing from the previous video, I'm going to make up some numbers and say we're titrating 100 milliliters of some acid of unknown concentration using a 1 molar sodium hydroxide solution. So that's the way we're going to set this problem up. We're going to do the titration of 100 milliliters of our acid with unknown concentration using 1.0 molar NaOH. Now, full disclosure, the numbers end up pretty unreasonable, but I wanted them to match the later examples that we're going to do where I actually got these pHs and everything from. So knowing what we know, we're going to set this problem up right here. And I've got it set up so we've got 100 mils of our acid of unknown concentration, 1 mil of sodium hydroxide. These pictures I drew out in advance because I knew I couldn't draw them out in real time, and they're based on numbers that I calculate in a later video. So, for instance, for the strong acid with strong base, I do a video that talks about calculating along a titration curve for HI with NaOH, and then we set up all these ice problems from some stoichiometry, and that gets me these numbers. In fact, I'll just kind of sketch them in. We had a starting pH of around 0.7-ish, and again, these are pretty rough, so don't look too closely. There's a little suspension of disbelief. And then we end up with like 0.8-ish, right, and 1 and 1.3, and then we jump up to 7, and this is a super duper important point, as we've discussed. We got like 12.6, so all of a sudden we get this huge leap, and then 13-ish, 13.2-ish, 13.3-ish. So this is the curve we end up with. And similarly, I did some calculations for a weak acid, HF, in a future video there. And those pHs started out a little bit higher, in fact, rather than leave those there so I can point. Our strong acid, same amount, same concentration, ended up being around 0.7 for the starting pH. This one ended up around 2. Okay, weak acid, less dissociation, less acidic solution at the same concentration. Then we had like 2.7, 3.1, 3.6, and it jumps up to a very important number, 8.22. And I want you to look there versus there. This is our equivalence point for our weak acid titration, and this is our equivalence point for our strong acid titration. And I talk about that a little bit in the videos, and we'll talk about it in this video as well. Then we end up with the same numbers up here, which is kind of interesting. So the 12.7-ish, 13-ish, 13.2, and 13.3. So after the equivalence point, these numbers end up the same. And when we talk about those calculations in the future videos, you'll find out it's because those pHs are entirely due to excess hydroxide ions. All right. After we hit the equivalence point, all of our starting acid is gone, and we have excess hydroxide ions. So these numbers, again, you'll see in a future video. That's where these lines came from, and those lines happen to match, or at least qualitatively match, these pictures we were talking about in the previous video. So now let's do some analysis of this. First up, in terms of differences, we mentioned it earlier, but this graph starts lower. It's a higher concentration. We've got the same volume, and we've got the same concentration, at least for this. So we've got a lower pH there. It's more acidic. We've got a higher pH there because the weak acid doesn't dissociate as much. Now, this is a fairly straight shot going up logarithmically. And then right here, we've got this bump. That's a hugely important difference in these, and we'll get more into it later. Right here, we've got our equivalence point at pH 7. Right here, we've got our equivalence point at around pH 8.2. And then after this, things end up the same. So the key areas where we're seeing differences are right at the beginning, along with this shape, and then the equivalence point right at the beginning, and then along this part right here, and then the location of that equivalence point. All right, so those are the key areas we'll have to address in differences. Now, in terms of similarities, this is the most important. All right, I set up our volume at the equivalence point as the same, 200 mils in this case, 200 mils at this case. I said that I started with 100 mils of these acids. My HF I started with as a weak acid, but 100 mils of a certain concentration. HI, 100 mils of that same concentration. So if moles equals moles, like we said for our titrations here, then they should be occurring at the same equivalence point, and they are. So we'll do that calculation, and then we'll jump back to these numbers here. I want to set this up. 100 mils of our acid with unknown concentration using 1.0 molar NaOH. We know that molarity is the moles of something over the volume in liters. And in this particular problem, I just told you we've got an equivalence point around 200 milliliters of our base. So something that I suggest to people all the time is write the equations and use them as a checklist. I then know this concentration right here. I know this from our graph, and so I can solve for that molar amount, right? So this number, and this number, and we do some rearranging there, and we find out that the moles are molarity times volume in liters. In this case, that's 1.0 molar, 0.200 liters from our graph, and that's 0.200 moles of NaOH. Now, I think without our spoiler alert that moles equals moles, this is kind of a stumbling block. But luckily we know moles equals moles. The moles of our base that we just used is equal to the moles of the acid that we started with. That's how you reach this neutral point, this stoichiometric equivalence point. So moles equals moles. Again, if you can walk away from anything in these titration videos, moles equals moles. We have some information about our acid. We know we have 100 milliliters of it. That's a volume. And we know we have a molarity. Sorry, we're solving for a molarity. We know these moles because it's right here. All right, so I'm going to check those off. And I'm going to highlight, we have the volume right here, and we have the moles right here. Okay, we just got them because our moles is equal to our moles. Our moles of acid is equal to moles of base. So we can rearrange our molarity equation, this time solving for molarity. Moles over volume in liters. Our moles in this case, 0.200 moles. And our volume in liters, we had 100 mils, so that's 0.100 liters. And we end up, in this particular case, with 2.0 molar our acid. I'm just going to write acid, because for the example I did two different acids. All right? So that is our concentration of our acid. We just solved the titration problem, and now I want to jump back and look at some key points on those graphs. So we should probably fill in this critical information that we just found. That is, we end up with 2.0 molar acid because we had 1 molar times 0.2 liters. So 1 molar times 0.2 liters for the NaOH. And that's going to be equal to our number of moles, 0.20 moles. And that's going to be equal to our 0.20 moles of our acid, 0.20 over 0.100 liters gave us 2.0 molar. All right. Moles equals moles. Now let's look at these pictures, and we'll talk about why the pHs are what they are and why this ends up with this. And I set up these equations in advance, and they kind of look like a mess, but they actually make sense if you squint for a bit. Green we're using as neutral, so NaI, sodium ions, conjugate of a strong base, those are going to be neutral. Iodide, conjugate of a strong acid, those are neutral. Water, neutral. Water, neutral. Sodium ions, conjugate of a strong base, they're neutral, and I labeled that and that as neutral part of the base. The iodine I labeled as the neutral part of the acid. And then we need to look a little bit at the F. The F is the conjugate of, F minus is a conjugate of HF, which is a weak acid. So this F is a weak base. And let's look along our titration at what we have, and we'll see why we end up with acidic and basic pHs at different times. There we go. All right, so what do we have in the beginning right here on both graphs? It's all of our acid. In this case, HI, and in this particular case, it's all HF. And since HF is weaker, we've got a higher pH. That's all there is to that. As soon as I start adding some base, I'm turning some of that HI into NaI and H2O. So after this point, all of a sudden, I have some sodium ions, some iodide ions, in addition to the HI I have. So in this entire region right here, in fact, in this entire region right here, and again, ignore the pH for this, is just in this volume region on that titration, I have sodium ions and iodide ions and hydrogen ions. So there I stopped to get a bigger red marker. So sodium ions, iodide ions, and the HIs we haven't used up. Since that's a strong acid, that's really H's and I's. So what we have at this point in the titration, we have H plus, or H3O plus, Na plus, and we have I minus. It would have been better if I had labeled those in our colors, but I can just declare neutral, neutral, acidic. So that solution's acidic over in that part of the titration curve. Now as we look at this side, as soon as we start adding some sodium hydroxide, the HF starts to turn into NaF. So we've got sodium ions and we've got fluoride ions. Now over here, the HI completely dissociated. Over here, it's not going to completely dissociate. In fact, it's barely going to dissociate. So we are going to have HF. And I don't know that that's something super obvious, but we have in this region HF. We've got a tiny bit of H plus, and then we're going to have our Na, which is neutral, Na plus, and our F minus, which is basic. Okay, so this is a weak base. This is acidic, and then that Na is neutral. So as we look at it, the acidic nature of this in general is going to overcome the weak base nature of the F minus, and so this portion, as we're looking at it, ignoring pH, but just this volume range in the titration, we're expecting to be acidic. When we reach the equivalence point, things change a little bit. We started with all HI, we added hydroxide until we got to here, and used up all the HI. So there's no HI left, there's no NaOH excess, so we just have sodium ions and iodide ions, which is why we end up neutral right there. And I'll put those in. Right here we've got Na plus and I minus. Again, both of those are neutral conjugates of strong things, so that's why we end up at 7 right there. After we pass this point, I can't make any more NaI, so if I add more NaOH, I just get more NaOH. And to be clear, at the equivalence point, all of the HI is gone. And we don't have any extra NaOH. That's why we only have Na pluses and I minuses. After that equivalence point, the NaI stays the same, and I just keep dumping in more NaOH, more Na pluses and OH minuses. So let's try and see here. We have OH minus, we still have Na plus, and we still have I minus. All right, and the Na plus is neutral, the I minus is neutral, and obviously that OH minus is basic. So this entire region, again, ignoring the pH, but this volume region on our titration curve, we expect to be basic. And in this particular case, our pH is going to be based on the excess base. So our pH for this entire region is going to be based on 14 plus the log of our concentration OH minus. So this is POH, so 14 minus the POH gives us this pH. So in this entire region, we've got the pH equal to that. In this entire region, we've got the pH just as the negative log concentration H3O plus, H plus. All right, so this excess H plus is our determining factor in pH over there, and this excess OH minus is our determining pH factor over here with a 7 right there. All right, so that's that basic setup. That's what we have present there. HI gets used up. Less HI, more H plus and I minus being reacted with the OH. Less H, less H, less H gone. More OHs excess. As we look at this right here, we just said we have HF undissociated and H plus. So when we find a pH here, there's something we really need to deal with. We have H plus and F minus, which is a buffer system. And I will have to grab a marker for that. As I discussed in another video, buffers are a situation where we have a solution that is a mixture of an acid, weak acid or base and its conjugate, and they resist changes of pH. And they do that by having species that are on both sides of an equilibrium expression. So I want to write the dissociation of this HF, the aqueous dissociation of that. We have HF in water. It's going to give us H3O plus, or H plus if you want to consider it that way, and F minus. If we look right here, we start to have, after this point right here, we have some F minus, and we have HF, so we have a buffer. Which means when we need to do those calculations, we can use the Henderson-Hasselbalch equation, and in those future videos I go through the exact details on calculating these points. But for right now, we want to pay very close attention to the fact that this is the buffer region. And there's a very important point in the buffer region, and it would be worth setting this up, well, I guess we'll put it right there. And I talk about this in the Henderson-Hasselbalch video, but 1/2 way to the equivalence point, your pH is equal to your pKa, or your weak acid. This is big information, so right here, and I realize that's turning into a colossal mess, right here, halfway to this equivalence point, which I've got is 0.20, so I'll label this right here. Whatever that number is, that is equal to our pKa, the negative log of Ka. And the reason for that is we have halfway to the equivalence point, half of our acid has been used and it has been turned into base, so our Henderson-Hasselbalch equation turns into, since pH is pKa plus the log of A minus over HA, if you have A minus and HA the same, that whole term drops out, and you get pH is equal to pKa, halfway to the equivalence point. All right. In short, you're going to use Henderson-Hasselbalch over here. Over here we had pH negative log of our H3O plus because it was strong, pH just based on OH minus. Here we're going to have to do ice. Okay, and I guess we can write that in. We're going to have to do ice at that point in our titration. Here we can use Henderson-Hasselbalch. And then over here, it turns out, what do we have present? Well, we have all of our HF used up, so we've got sodium ions, and we've got fluoride ions, and then we've got the extra NaOH that we added. So we've got our fluoride ions, we've got hydroxide excess, and we've got sodium ions. And things that are determining here, this is what determines our pH. Even though the F minus is a base, the OH minus is our strong base, and that's our excess. And so our pH, just like it was over here, is going to be the negative log, 14 plus the log of our concentration of OH minus. All right. So in terms of finding our pHs at different points in the titration, this is going to be done as the negative log concentration H3O plus, along with every single point right there. This is going to be a 7, and then negative log of hydroxide we're going to use to get the pH there. In this one, from the equivalence point on, we're going to use 14 plus the log of OH minus, using the POH to get the pH, because it's still just excess OH minus. Here, when we start out, we're starting out with a weak acid. We're going to have to set up an ice problem. Right here, we have just F minus and Na plus. So if we have F minus and Na plus, then in order to deal with that, we're going to have to do ice. Okay, so we did not here, this was just 7. Over here, we have to do ice. That's a weak base, that's neutral, and so that's a hassle. You'll look at the other videos that I did and you can see exactly how I do that. And then after that point, we've got negative log. So the short of it, I know this looks like a mess. Negative log H3O plus, 7, 14 plus log OH minus, ice, Henderson Hasselbalch, ice, negative log, 14 plus the log of OH minus. And those are how we get the calculations in the different pH regions. And again, since we have this F minus here and it's a weak base, that's why our pH at the equivalence point for a titration like that ends up being basic. In this particular case, it was around 8.22.